Okay, thank you for your introduction, and thank you everyone for listening, for coming. This is the project I completed alongside with my friends from Tianjin University and Tsinghua University, and I'm truly delighted to share it with all of you. We introduced AlloyStack, a library operating system for serverless workflow applications. Nowadays, serverless workflow are gaining significant traction in today's tech landscape. They serve as a adopted model for designing and executing tasks in production environment, such as image processing and financial analysis. Globally, in Asia, the top 5 frequently invoked workflows account for 46% of total invocations. This makes optimizing the performance of serverless workflow a crucial focus. There are two characteristics of serverless workflow. First, serverless workflow rely on small single-purpose functions. These functions are short-lived and light-weighted, making cold start problem more important as each function may experience its own cold start. Second, these functions depend on each other and need regular and large amount of data exchange. This leads to significant communication overhead, leading to inefficiency. To accelerate workflow execution, OS level improvement must be leaded, must be done to address both cold start latency and data transfer inefficiency. However, the current software stacks cannot meet both requirements. While higher level abstraction ensure isolation between functions and the kernel, they introduce additional layers that cold start and data transfer must go across. As you can see, current work specializes the runtime by removing unnecessary components, making the stack thinner or shorter, thereby reducing these costs. However, from our perspective, it is still far from efficient. So why specialized containers or micro VM starts slowly? The micro VM approach frames the device model by removing features that are not required for serverless workflows, such as BIOS, legacy devices, and PCI. However, it still include all major components of gas kernel. As you can see, here are about a second startup latency in gas kernel. Our analysis show that many functions do not require the full kernel. For example, most functions in serverless bench only require 3 to 5 modules. Therefore, specializations on kernels must be included. The library operating system approach divides the operating system kernels into several small libraries and compiles each function with only necessary components. As you can see, the startup latency of Unicraft, a libOS for cloud use, is much shorter. However, in workflow with multiple functions, small libraries are often reused, and in dynamic workflows, dependencies can vary a lot, making redundancy. By completely removing the gas kernels, routines reduce the startup time even more. But this removal can lower the isolation since system calls can go directly to the host kernel. It becomes more vulnerable to attack. To, to address data transfer problem, we measured 4 common data transfer methods, including inter-VM TCP, inter-process TCP, shared memory, and function call. The function call methods outperform the others a lot. This is because threads can naturally share the address space without syscalls, allowing the CPU to access data more efficiently compared to complex kernel functionalities such as sockets and memory mapping. This motivated us to use a single address space for serverless workflows to improve data transfer efficiency. In conclusion, the multiple small-sized functions and the dependency in serverless workflows cause cold start and data transfer bottlenecks in end-to-end latency. As a result, we present a library operating system with on-demand loading and reference passing for serverless workflow to tackle both of the problem. And now let's talk about our work, which has low start latency, efficient data sharing, and function level isolation with multiple language support. The right figure shows the architecture and the execution steps for of AlloyStack. AlloyStack is deployed as process across multiple nodes, receiving no invocations that are load balanced by a gateway. Here is the first step. In each AlloyStack process, there are three components: the standard library layer ASSTD, the kernel functionalities layer ASLibOS, and the global runtime layer ASVisor. Note that this ledger is different from those in hypervisor, gas kernels, or container systems, as they are not separate into different virtual address space. So let's make it detailed. Here is how we support kernel functionalities through ASLibOS ledger. We implement various kernel service in user space, such as the file system and network stacks, and so on, as multiple libraries. Since all kernel abstractions are in user space, host kernel security can be guaranteed. Similar to other programming language, programming platforms, ASSTD provide a standard library designed for the three main purposes. First, it intercepts user function syscalls requests and routes them to the syscall handler of the libOS. Second, it provides an easy way to use all features. As you can see, for users who want to go on AlloyStack, he can only replace the original STD use to ASSTD use, and all the features will be automatically used, including the reference passing and the on-demand loading. Thirdly, ASSTD is also responsible for switching the MPK access permission for system security through a trampoline code segment. We design a global runtime layer ASVisor, which includes a watchdog for HTTP requests, orchestrators for start the function, and monitors essential host resources, and a module loader that can load the module on demand. The right figure shows the loading process when function A calls the open interface multiple times. Initially, no modules are loaded. When a need to call open function, it first passes through the interface provided by ASSTD, and it emits an entry maze, and it tells the advisor to load the FT tab from the image. And after FT tab is loaded, STD records the address entry for the open, and as a result, invocations for open by A afterwards do not trigger any entry miss. And this can be also applied to another function that in the same workflow. AlloyStack provides a dedicated communication API as buffer for such transfer between functions in workflow. We introduced a slot parameter in as buffer API. Here you can see an example of using the as buffer API. The function A just acquire as buffer and write a EUROSYS conference data in the conference slot, and function B will read it and do some preparations directly into the buffer. We further support multiple languages through Watson. We implement the WASI APIs on our ASTD and fully move the Watson runtime as a function image. In this way, both C and C++ language and Python scripts are supported. After that, we additionally add our AsBuffer interface to C and Python to enable reference pathing. In the evaluation part, we will answer 4 questions. Do our on-demand loading methods help the cold start optimization? Is the data transfer process efficient? Do our speed up the end-to-end latency for workflows? Does this speed up works for functions in other programming language too? So we did our experiment on an Intel machine with 3 synthetic members and 3 real-world applications. And we carefully choose all the SOTA and relevant works into account for comparison, including Unicraft, gvisor, Wasmer, and for Rust-supported workflow, we choose OpenFuzz, and we re-implement the fast lane in Rust for fair comparison. And finally, we choose Fasten for Wasm support workflow. On the cold start latency, as you can see, AlloyStack can reduce the cold start latency to 1.3 milliseconds while ensuring kernel isolations. Since Wasmer and Fastlane support deploying multiple functions as threads within a single address space, we also measure the thread startup latency and label them as WasmT and FastlineT. We then evaluate the intermediate data transfer. For Fastlane, where it transmits data through reference passing by default, it switches to IPC mode when multiple functions need to run in parallel. Therefore, in this experiment, we also evaluate the data transfer latency under IPC mode. For OpenFast, we use Redis to transfer data. It shows that AlloyStack can reduce the data transfer latency by 1.8 to 2.6 times. We compare AlloyStack with Rust-supported workflow runtimes to evaluate the end-to-end latency of real-world applications. For OpenFast, we additionally tested gvisor environments where containers are replaced with gvisor sandbox. While maintaining kernel-level isolation, AlloyStack demonstrates 1.2 to 114 times reduction in end-to-end latency. We then rewrote all benchmarks in both C and Python and compared AlloyStack with Fasten. As you can see, in word count and function chain application, our implementation in both C and Python significantly outperformed Fasten. However, in some parallel sorting test cases, our approach was slower, which is because our Wasm runtime is like 30% slower than Fasten use. At last, we also did a breakdown of our system. It shows that on-demand loading reduced latency by 40 to 48%, while reference passing can decrease the end-to-end latency by 35% to 51%. So, in this work, we present AlloyStack, a library operating system designed to optimize serverless workflow applications. Our work are also open source under the Tanksys on GitHub. If you like to use that, just be free. Just feel free. Okay, thanks for listening.
Thank you very much.